Hello, we're going to talk about basic color theory today. So really what we're going to kind of get into is, what is color? How do we see it? And then how as printers can we understand it a little bit better so that we can incorporate some of the ideas of this into our process. So basically what it boils down to is like, if you want to reproduce color very well, you need to be able to understand how color works and some of the science behind this. And hopefully this little presentation will help you better understand that. So, we live in a world of color, and color is all around us. Something we experience. It's something that, we probably take for granted. It's something that has always been there since we were, able to see. And it's not something that we have to put a lot of thought into. So, but what we really got to understand is like, well, what is this color, and what does it really mean? What's the, how does it actually work? So our eyes are stimulated by light of many different colors. And so all of what we see and what we experience is due to stimulation in our eyes from the light that we see. So we need to kind of understand light a little bit better. There's different ways of defining light. And, if you ask somebody, what does light mean? I think they could come up with something. So these are some of the things you might see. Something that makes vision possible. Definitely a good definition. The sensation aroused by a stimulation of visual receptors. Okay, that's sounding a little bit more scientific, but let's blow you away. An electromagnetic radiation. Okay, like who's going to say that? And like, doesn't that sound terrifying? An electromagnetic radiation? That's what light is? No, it's not. Light's, that sounds dangerous. Light's something that's completely inert, something that doesn't hurt us. Well, let's clarify that last statement just a little bit. So in all actuality, light very much so is an electromagnetic radiation. The thing is what you've got to understand is that radiation, while we kind of think of it as a very negative and bad thing, there's a lot of radiation that we encounter on a moment-to-moment basis, and it's something that actually enriches our lives very much so. So what we're looking at here is what's called the electromagnetic spectrum. So, there are definitely some things on here that are, kind of scary. You got things like gamma rays. I mean, heck, that's what turned the Hulk into Bruce Banner into the Hulk, right? We want to avoid that. That sounds horrible. Cosmic rays. Yeah, that stuff will give you cancer in a heartbeat. We all know that X-rays, aren't the safest things to be around on a regular basis. They put those lead vests over you at the dentist whenever they take pictures of your teeth. So, ultraviolet, there we go. We got to put our sunscreen on to protect ourselves from the sun's rays. But just past ultraviolet radiation is the visible spectrum, okay? Which is kind of funny. We go from something that, when exposed to, it'll cause us cancer, to this very safe area that we experience on a, all day long, every day of our lives, which is the visible spectrum of color. And what this really is the radiation. Now, when we say radiation, all radiation is an oscillating energy. It's something that has peaks and valleys in it, and it is repetitive and it oscillates. That's all it is. It's just energy. It's just it's packets of energy. That's all it is. Now, how much energy it has is what determines on whether or not it's, unsafe or not. But if we also look at this other, if we continue along down the spectrum, we have things like infrared, television waves. You got radio waves, infrasonic, sonic, ultrasonic, radar, all these sorts of things. And these are things that, are passing through our bodies all day long and causing no harm. So what we have here is on this side of things, it's very low energy, and on this side of things, it's very, very high energy. But the visible spectrum is kind of about in the middle right there, and it's something that we probably understand and interact with the most. So when we look at the visible spectrum right here, we have a rainbow, and and this is kind of how the spectrum works, and we'll kind of get into a little bit more depth as we move down the line. But what I want to just kind of break down to you is that we've got red, orange, yellow, green, blue, indigo, and violet. And that's those are the colors of the spectrum. And the way that I remember that is Roy, R-O-Y, Roy, G for green, and then Biv, blue, I for indigo, and V for violet. And that's the spectrum and how that energy changes. So just like on one side of the electromagnetic spectrum, we had more high energy on the left side and lower energy on the right side. Well, the same thing is occurring with the visible spectrum as well. So as we move across the spectrum, we're going to have more energy and less energy. So, and how do we talk about, like, when I say energy, what does that mean? Well, if you go back to what I said about radiation, is that it's it's an oscillating packet of energy. So that oscillation creates wavelengths, and the closer that the wavelengths are together defines how much energy they have. So longer wavelengths are going to have less energy, and more compressed ones are going to have more. And that's basically how it works. Inside of we'll get into how our eyes see it in just a second. So all of this, was first theorized by a very intelligent man named Sir Isaac Newton. So he was a physicist, and he made a lot of theories. He's probably most famous for the theory of gravity, but what he theorized was the idea of white light containing all of the colored light that we see. And let's look at and we call that the additive color theory. So that's what he theorized. And basically what the additive color theory is just that white light is actually a combination of all colors of light into one. And let's take a look at an example that might make this make a little bit more sense. So if we have red, green, and blue light, and we shine it, let's just say they are filters over flashlights. We take those through and we shine them onto the wall in a dark room. What we're going to see when we overlap them all is that it's going to be white. Now, let's just clarify something real quick before we jump any farther. We're talking about light here. We're not talking about inks or paints. If we took red, green, and blue ink or paint and we mixed it all together, it sure as heck isn't going to make white. It's going to make a dirty, ugly brown, right? So let's clarify that we're talking about this is how light works. And this is how, we experience color. So red, green, and blue combines to make white. If we take red and blue and we combine those, can you take a guess which color that's going to make? Oh, we go and we blend them together and they make magenta. They make a nice bright pink. Magenta. Okay. And then if we take blue and green, we mix those together. You got a guess of what they might make? Let's see. Oh, they make a nice light blue. We call that cyan. Huh, look at that. Next, we've got red and green. And this is probably the trickiest one. The other ones you could have probably guessed, but, most people are very surprised when we say that red and green, when combined, make yellow. Because we very much so know if we took red and green ink or paint and mix them together, it's going to make a god-awful ugly brown. It's going to make just atrocious color. It's not going to make yellow. But again, this is the way that light functions. And then if we bring it all together, what we see is that we've got red, green, and blue. And then whenever they interact, we've got cyan, magenta, yellow. And then when all three come together, they blend to make white. So that's why it's called the additive color theory. That whenever we add red, if we add red to green, it makes yellow. If we bring red to blue, it makes magenta, and blue to green, it's going to make cyan, because they add together and they build to make white. That's why it's called the additive color theory. Now, another thing to kind of consider is that we have what's called the subtractive color theory. Now, and it works in the opposite manner. So when we think about this, is that so when these colors add together, they make these. They add to make these, but these right here, what they do is they work inversely, because we print with yellow, magenta, and cyan. We print with those, and we print with that on top of white paper. So think of it this way: is that with cyan, magenta, yellow, and black, of course, when we lay that on top of a white sheet of paper, they act in an inverse manner. They act in a subtractive manner. So if we start with white, which is, all color, let's just say it right there, and then we add yellow to it. Well, if we add yellow, let's go back to actually this image. So if we have yellow is a combination of red and green. So if we have yellow, what that means is that we do not have blue. We do not have blue. So we can kind of start thinking about color in this way, that if we have yellow, we do not have blue. If we have cyan, we do not have red. If we have magenta, we do not have green. So that's essentially how CMYK, the theory of the subtractive color, how that works is that we start with white, and then we add the yellow, we add the cyan, we add the blue, and that subtracts away from that sheet of white. So by subtracting away, if we, in theory, if we have equal amounts of cyan, magenta, yellow, it's not going to add up to make white, it's going to add up or subtract away that black. Okay? So if we have cyan, magenta, yellow, that means that we do not have white. Now again, this is theory. We always add in black too because, inks aren't as optically pure as science. We've done our best to make those inks as optically pure as possible, but it's just not there yet. So, and just like I said, you cannot mix inks the way we do light. As we know, and I already mentioned that when we bring these things together, they don't, inks and light doesn't work the same because they're not optically the same, and that's what makes them different. So let's talk about how light interacts with ink. It can do one of three different things. It can be transmitted, reflected, or absorbed. So let's look at this. So in this particular example, we show that red, green, and blue light, which another way of thinking of red, green, and blue light is just white light. White light is striking a surface, and some of that light is passing through. The red light is passing through. So in this particular instance, if we have red, green, and blue light hitting a surface, and the red light is transmitting through, what color is this surface? Let you think about that for just a second. All right, there's no trick to it. It is a red surface. It's a red surface because red red is essentially the opposite of cyan. What makes cyan? Green and blue. So it's red. You know, think about if I put on red sunglasses, what's everything going to look like? It's going to look red, right? So, and what that basically means is that cyan is being absorbed. And another way of thinking of cyan being absorbed is, well, green and blue is being absorbed. So all of these things kind of like play together. In this particular instance, we got white light that's striking a surface, and red, green, and blue light is reflecting off of it. So that's reflection. So that's white light reflecting white light off of a white surface. And then the last way that light can interact with a surface is absorption. So light strikes the surface, it absorbs, you know, the red, green, and blue light, the white light, and then it absorbs it, does not reflect anything, and we perceive that object as black. So when we deal with ink, there's a lot going on here, and I think, or at least a lot more than we would normally give it credit for. So if we have white light that's coming down and it's striking, just a layer of yellow ink. Now, when we use process color inks, our inks are transparent. They are designed to allow light to pass through, but it's a yellow layer of transparency. So what happens is that white light comes through, strikes the yellow, goes through that yellow layer, hits the white layer, the white substrate, and then it reflects off of it. Now that yellow layer goes and absorbs all, which color? Blue. It goes in and absorbs all blue. And then what it reflects is red and green. The thing is like our eyes absorb that red and green light, and we perceive that as yellow. And that's how, and that's essentially how it works. It sounds a little overcomplicated for what it is, but what I want you to understand is that when we are printing process color, the light passes through and absorbs a color, and then it reflects off. It doesn't reflect off of the top. A lot of people think that it's white light coming and striking the top of the yellow layer, and then we just view yellow. There's actually more going on. We're hitting it with white lights passing through, it's striking that white background, reflecting that yellow layer, stripping away all the blue, and just green and red light are reflecting off of it. So yes, it doesn't necessarily reflect yellow light, it reflects red and green. And by reflecting that red and green, we interpret that red and green as yellow. So, another way to think about this is that if it just reflected off that top layer, if we printed yellow and magenta and it just reflected off that top yellow, then all we would see would be the magenta. So what happens is white light comes and strikes, it passes through the layers. Those layers reflect, their correlating color, like magenta absorbs all the green, yellow absorbs all the blue. So what is reflected is red, because that's the only one that's left. And that's how process color works, by subtracting away certain areas of that full visible spectrum. So, one way to kind of think about color, and kind of like, I don't know, it's something that's very commonly done, is the idea of what's called the color triangle or the color wheel. The thing to understand about this is that, wherever you see a secondary, one of the subtractive colors, like yellow, whatever point is opposite of that is the the color that it filters out. And then also, when you have the additive colors, whatever's in between it is what the two colors blend to make. All right, so that's essentially something you need to understand. If you don't have a color, a light color wheel just memorized in your head, it's something I highly recommend putting in your brain, because this is something that if we're going to go create some really nice looking color, this is something that we need to be thinking about and be able to reference very quickly. Okay, so something to study. So let's talk about how do we measure color. You know, we see it, we experience it, we now have a little bit better understanding of how the science of it works. Let's talk about how we quantify it. Well, the first thing to do is to talk about density. Okay, so you know, density doesn't really measure color. It's more of it's a measure more of, let's say, intensity. I think is a better word. So density is essentially whenever we do a measurement, a density measurement, it is a number that it gives us that describes how much light is being absorbed by the sample that we just measured. So the higher the number that we get, the higher the density, that means the more light is being absorbed by that sample. So if more light is being absorbed, that means that it must be a darker sample. Okay? So what I want you to kind of understand about density is that if we do a measurement, the higher that number is, generally the darker it is. Now, a lot of times what we'll do is that we'll do density measurements on various different colors. That won't tell us, what color it is, but what it will tell us is essentially how much ink is being printed. So if that density number is higher, when we measure it, it's telling us that a lot of ink's being laid down. If it's a lower number, that means less ink's being laid down. So it's a way of just documenting how much ink is being printed based off of, whatever our combination of variables may be. So it's more of a way of just kind of monitoring what's going on, and also a way of documenting, or quantifying how much ink is being printed. And that's really what density is used for. Another very common measurement device is the eye. So another one that we definitely take for granted. So the thing to understand about the eye is that inside of the back of our eyes there are receptors. Those receptors are called cones. So the color receptors are called cones. And I use that, and that helps me remember it, because color, C-O, cones, C-O-N-E-S. So cones, that's how I remember that sort of thing. Can you guess there are 3 different types of cones. Can you guess what 3 they are? Well, it's red, it's green, and it's blue. So those are the 3 cone receptors we have in our eyes. So basically what happens when we see color is that light comes in through our pupil. Light comes in, it strikes the back of our eye. And in the back of our eye is where these cones are. And let's just say that what we're looking at, the color that we're looking at is red. That's the simplest one. So we're looking at red. So what happens is that these red receptors get stimulated. That stimulation correlates to our brain. And in our brain, due to that stimulation, interprets, what we're seeing as red. So same thing happens with green and blue. So if we look at something, let's just say that is yellow, we're looking at, bright yellow car, let's say, or school bus. So when we're looking at that, what's happening is that red receptors are being stimulated as well as green receptors are being stimulated. So they're both being stimulated, and that's sending a sensation to our brain. Our brain interprets that sensation as the color yellow, and that's how it works. Now there's another type of receptor in our eye. It's called the rods. The rods, so we have rods and cones. So cones detect color, whereas the rods, they more make out detail. So they don't really interpret color, they make out detail. And the rods are actually a lot more sensitive than the cones. So just kind of maybe put this stuff in your mind in everyday kind of use, is that when you're laying in bed, you're trying to go to sleep, all the lights are turned off, but maybe there's a little light coming in through the window from a street light, or maybe you've got a an alarm clock or something, or a computer in the distance that's shining a little light in the room. But what the thing is like when it's really dimly lit, look around the room, and what the thing is you'll be able to make out shapes and forms, but you won't be able to see any color. And whenever you're in an environment like that, you're seeing strictly off of the rods in your eyes. Because again, the rods need a lot less stimulation than the cones do in order for you to be able to use that stimulation to see. Okay, so those are the rods and the cones. Very important. Now the other thing about the eye is that the eye is connected to the brain. Okay, and the brain is a complicated thing. But you guys have probably heard about this at some point, is that there's two sides. They say that there's two sides to the brain, and the different sides of the brains, work with different concepts. So the left side of the brain works with things like language, logic, numbers, sequence, linearity, analysis. So this is like, the real, let's just say the science side of the brain, science and math side of the brain. Then on the right side, you've got things like rhythm, music, images, imagination, daydreaming, color, and dimension. So color is over on this side, and this side is more of like the creative side of things, So that in itself kind of causes a little bit of an issue. What I mean by that is that, a lot of times when we're trying to communicate color, it's difficult. If I was on the phone and I was calling a client and that client, is trying to describe a color to me over the phone, if they're trying to say like, I want this very particular purple, and I don't want it to be too light. I want it to be kind of, I don't want to be too saturated. I don't want to be too blue, but I want it kind of more on the reddish side of purple or whatnot, and they can say all that stuff. And maybe I can kind of get in the ballpark of what they're saying, but I can't, they can't communicate that directly to me, because what they're trying to do is they're trying to communicate something that is more creative. They're trying to put, a number to something that usually doesn't have a number. So that in itself is why, why we have a lot of problems with color. Color is something that, like, nailing and getting exactly right every time is something that is kind of difficult to do. So, and the other thing is, like, the brain can be tricked. So here's a little trick right here. So what I want you to do is I want you to stare at that X, and I want you to stare at it. We're going to look at it for about 15 seconds. And basically what we're going to do is we're going to just we're going to trick our brains, and when we trick our brains, that might give us a little insight into, how our brains necessarily can't be trusted when it comes to color. So keep looking at that X, and boom. So what happened? What happened? Essentially, our eyes got fatigued. Our receptors for red and blue, they got burnt out. They got overstimulated, and then all of a sudden that stimulus went away, and what we wind up seeing is a latent image. The situation with that, when we think about it, that could cause problems. Essentially, our eyes don't see things perfectly, which means our brains don't interpret colors perfectly. Let's try another example. This one's pretty interesting. So again, just stare at that at that white X, and we're just going to stare at that for about 15 seconds, and a very similar thing is going to happen. We're gonna fatigue out our cones, and it's going to give us a latent image, and it's a pretty cool special effect right there. If you haven't ever experienced that sort of thing before, it's kind of neat. So basically, what we're dealing with is that we're fatiguing our eyes. If we're tired, we might interpret color differently than if we were bright and vibrant. If we were outside looking at color, we might look at it differently than if we're inside. So these are things to understand. Also, we don't have the best color memory. We kind of think we do. We think we can recall color very well, but that's not always the case. And this next example kind of illustrates that. So if we look at this one right here, and we compare it to the next slide, does that color look the exact same? So if I go back, so here we are originally. That color looks kind of dark. And then when I come here, that color looks a lot brighter. Very much so, it looks brighter. So it looks like two completely different reds, but you know this is a trick, and they are the same exact reds. So yeah, we're very much so influenced by the color that surrounded that red. So we weren't really addressing that color properly, or we weren't, evaluating it properly because we were being distracted by the background, and that background very much so influenced how we viewed and understood that red color. So check this one out. This one, it's kind of the same idea, but we can see it in live time. If I look at this, I know this trick, it's a trick, but the red on the left side looks darker. It does. You can't argue with me right now that if you look at these and you compare them left to right, which one looks darker? You're going to say the one on the left, even though it's not. But you can't turn that off in your brain. I can't turn it off in my brain. I know that's the exact same, but I can't turn it off unless I do something like this. So when you see it this way, it's very clearly understood that that's an issue. It's very clearly understood that it's the same color, but beforehand we cannot tell. Okay, so we can't always trust our eyes when we're evaluating color, and that's, I think, the big takeaway of what we're kind of going through right here. You should always compare colors side by side and not set them on top of each other. So if you're trying to compare color, a lot of times what people will do is they'll take two samples and they'll overlap them and compare them between each other. It's not a good way to do it. Set the two samples on similar colored backgrounds, probably something of a neutral color like a white or a gray, maybe even possibly black, but put them on the same background and compare them side by side, not overlapping each other or overlapping any other colors for that matter. That's what's going to help you make better judgments if you have to base it on a visual match. So let's talk about color in the brain. Like, how does color work in the brain? Well, it's based off of three different attributes of color: lightness, chroma, and hue. And this is how our brain, processes color. So the lightness value of a color is essentially like, how light or dark is it? Is it close to white? Is it close to black? Is it somewhere in the middle? How light or dark is a color? Okay? It's the lightness attribute. The next one is the chroma. Another term for chroma would be saturation. They're two words that can be used completely interchangeable. It just depends on who you're talking to. So chroma, there's some parts of Photoshop that use the term chroma, and there's also parts of Photoshop that use the term saturation. So there are areas that and it's the same thing. It's the same thing. It's just two words that are used interchangeably. So this is going to be, the colorfulness attribute. I like to think about it as, how pure is the color? Another way to think about it is a color's deviation from gray. So if we have, if you think about that L attribute being over here, the farther that it moves away from gray, the brighter and more pure and more saturated that color appears. So I think, chroma, a better way of kind of thinking about chroma or saturation is like, how far away is this from gray? How far away is this being like muted out? And that's really, in my opinion, the way to kind of think about saturation or chroma. Next one is hue, the qualitative attribute of a color. So, the best way to kind of think about this is, I've looked up hue in so many different, web searches or dictionaries, and finding a really good definition of it is difficult. I've even seen the definition be the color of a color. But the thing to think about, what it really means is like, when we talk about that Roy G. Biv, that spectrum of color, where does it fall? Is it essentially a blue shade? Is it a red shade? Is it a green, yellow, cyan, magenta, whatnot? So think of like hue, whereas shade is not the best word, but I think in normal, layman's terms, that's what we refer to as the shade. But the better way of thinking about it is hue. Okay, so hue is the proper term. It's like what category does it fall into? So when we talk about measuring color and putting a number to color, a very good way of doing so is using a perception-based tool. It's a system that is directly related to lightness, chroma, and hue. Since that's the way our brain interprets color, why not measure color in a way that kind of matches that by using these three attributes of the color and putting a number to each one of the three. And that's what we've gone and done. Or I say we. That's where scientists have gone and done it. And they created something called CIE LAB. CIE stands for Commission Internationale d'Éclairage, which is French for the International Commission on Illumination. So this is an idea and a concept that's been around for a very long time. I believe it was, don't quote me on the date, but I believe it was like 1936. I think in the 30s. I'm pretty positive it's in the 30s, but I want to say 30s. I could be wrong, but it's right around in that area. It doesn't really matter, but what I wanted you to know is that these ideas have been around for quite some time. And basically, what CIE LAB is a way of graphing color based on three axes, and those three axes being L, A, and B. So when we look at this, going in and out, up and down in the center is our L axis. On the top we've got 100, on the bottom we've got black, it's 0, and then we have the A and B axes. So the A axis is the green to red axes, whereas the B is yellow to blue. And the way that I remember which one's which is that the A axis is for apples. Apples are red or green. So the A axis is red and green. And then the B axis is bananas and blueberries. Okay? So that's how I remember what the axes are, is that A for apples, red and green, and then B is for bananas and blueberries. Okay? And silly as that sounds, I find myself referencing that silliness on a regular basis. So this is just a way to graph it. It's a three-dimensional graph. So if we were trying to plot out a color, there would be an L, reference point. There would be an A reference point and a B reference point. So let's see how this actually works with samples. So let's say we've got this package, Vegafruit package. All right. And we go and we take 3 or 4 measurements off of it. Okay. And, so we've identified, these 4 colors that come off of it. So the way that this works is that it would be, again, graphed on different locations of the LAB sphere. So then, it not only would be graphed on, the A and B, but also the L. So we'd have a reference number for each one of these. So we graph it on the L, we graph it from the A and the B as well. And then that would be a reference point for that particular color. Okay? So another thing that I wanted to just kind of point out about CIE is that CIE is hypothetical. It's like the perfect color space. What I mean by perfect is like, if it's a color that we can measure, it's a color that's going to pop up in this color space that we have created, or that was designed by the CIE. So that's LAB. Now there's some other versions of this exact same idea. We have what's called the LCH, and L, lightness, chroma, hue. And this one, it's, there's some people that really prefer the LCH. And the reason that they like it is because of the angle. And the angle kind of helps them keep in mind like what hue is. So some people like the LCH because it's a little bit easier for them to just look. And if they just know, if they kind of have an idea of how it goes around 360 degrees, that, they can imagine what 24 degree is a whole lot better and easier. Just kind of get them in the ballpark of thinking about color, a whole lot easier than this one. Because when you start doing, these, it's not quite as easy to kind of visualize and well, let's just say memorize. I mean, you can kind of think about with LCH is that if you can kind of remember that, between 0 and 90 is red to yellow, depending on where that hue angle is, it'll help you kind of just visualize things a whole lot better. And the term hue angle pops up a lot as well, especially when it comes to matching colors and, the quality of a process color ink. And I'm not going to go into all that right now, but if you ever hear hue angle, if you ever hear that, anywhere, what that's referring to is just, it's, where in the sphere does it fall, So, and when we look at it here, it's just, people that work in color on a regular basis, they can remember these angles, or at least kind of get them in the ballpark pretty easy, by remembering these kind of quadrants. And it's just a whole lot easier to visualize and to memorize on the top of your head. So, but essentially the thing to understand is that these color spaces are, they're a much better way of describing color. Because to think about it, like up to this point in your experience in documenting color or communicating it, you've probably done it one of two different ways. You've maybe gone and picked out a color from a Pantone book, and that's a good way. It's a real good way because now we have, we can pick out a particular color, and there's a very known value associated with that color. So that's a good way. It's a very good way to communicate. It's one of the easiest ways to communicate accurately to another person. As we go back to that phone call I was talking about before, if they're trying to describe a purple and, and I can't quite figure it out, or I will never envision it exactly how they are. But if they go, I want Pantone 265, I can go look that in my book and be like, oh, I know what color you're talking about. So that's a great way to communicate color. So that's one way that you may have done it. Another way that you may have done it would have been mixing a color in Photoshop. Okay? Let's take a look at something real quick. So if I was to, I'm going to bring up a file I had open. Where is mine? There's mine. Oh, my mouse is acting funny. Let's see, open recent. Here is a file that a student had earlier. Okay, so let's just talk about this for a second. So if I look at this, let's just say I've got this shape right here. I'm just going to pull it over to the side so that we can just look at it on our own. So we have that color right there. You know, it's a blue, right? Or I mean, kind of a purplish blue, right? So if I copy this and I go over to Photoshop, look, I've already got it pasted in here. Doesn't it look a little bit different? I mean, in my personal opinion, like if I look at it here versus I look at it here, you know, the color looks, I mean, not drastically different, but a little bit different. You know, in fact, let's just for you know, interesting sake, there's a utility on Macs that's called Digital Color Meter, and it's a way for you to go and just measure colors. So if I come here and I measure this in Photoshop, you know, one thing, it's like I move around here and okay, so let's get right in the center, right there. So 99, 96, 163. Let's go over to Illustrator and see what it reads for in Illustrator. So 99, 96, 163. So I go back over to Illustrator. Let's bring my meter back, and I come in and 98, 96, 193. All right, well, let's see. And then let's bring that meter back. 99. So it's a little different, not a ton different, but it is, well, it depends on where I am. So it's a little different, but it's not perfect. And it's the same exact color that I moved between Photoshop and Illustrator, and it's slightly different, okay? I mean, if between Photoshop and Illustrator can't keep things straight, then how am I supposed to? And so, and this also kind of goes back to why the second way that we've probably communicated color from each other before is through using RGB or even CMYK. So a lot of times you've probably gone over to, you know, Illustrator and like, oh, I'm going to make up a new color. I'm going to go make a circle right here, and then I'm going to go over to, and I'm going to go mix it up, you know, based off CMYK. Oops, I mean, sorry. You know, I'm going to go mix it up using CMYK and whatnot. And I'm going to mix that up, you know. So the thing is that's one way to. But here's the situation. Here's the problem with using CMYK or RGB to you know, mix or communicate color, is that whatever you mix up and the way that it's being interpreted by the user is going to be completely dependent upon the machine that they're using. Okay, so here's another example. If I take this file, I save it, and I take it home with me, and I open it up on my laptop at home. The thing is like when I open it up, all the RGB numbers are going to be the same. The CMYK numbers are all going to be the same. All those are going to be the same, but it very well might look different. I mean, let me ask you guys this. Have you ever looked at a file at school and then taken it home and looked at it on your laptop and it looked a little different? Well, the thing is like it looks different. You interpret it differently, but the numbers are the same. So how are the numbers the same if they don't look the same? So, and that's why, you know, that's not a very good way of communicating color. What we need is an external evaluator to measure that color. And that right there is what a spectrophotometer is for. That's how a spectrophotometer measures color. It's like, it's an observer that has no opinion of it whatsoever. There's nothing to be influenced. You know, it can't be influenced. All it's going to do is that spectrophotometer is going to measure a color, and then it's going to measure another one, and then you can compare the two. Each way, whenever it's measured in LAB or LCH. So, and what those numbers give you is, you know, an unbiased external observer of the color so that it's not impacted by whatever device is producing it. So when we go back to the idea of your school computer versus a laptop, how those colors might be different, what you could do is that you could measure one of those colors with, or one of those samples with a spectrophotometer, measure the other sample with the same spectrophotometer, and see how those numbers compare. So, long story short is that, understanding that and being able to navigate through that is what color management really is being able to understand or how to evaluate color independently from a device. We're not going to get into that, but what I want you to understand is that whenever you measure color using CMYK or RGB, you're only getting a color that is accurate on that same device. Now, one thing I can probably depend upon is that if I've got this file right here and I save it onto my computer, I come back tomorrow, I open it back up, that color is going to look pretty exact from yesterday to today on my device. But it's not always going to be the same if I take this image and I send it somewhere else, especially if I send it to another computer, but even worse, if I send it to a color printer. If I send it to a color printer, is it even going to be in the ballpark of what it looks like on the screen? I mean, it might still look purple, but it's going to look like a very different purple. So, and that's what spectrophotometer is so useful for, is that it can give us an evaluation between, one output device to another, and it's not being impacted by the device that produces that color. So that is my little breakdown on color and whatnot. So just in review, a couple things that we hit upon is that we've got the additive and subtractive color theory. The additive color theory is that we've got red, green, and blue. Red, green, and blue add up to make white. We have the subtractive color theory, which works on an inverse. We have cyan, magenta, yellow, and those three colors filter away from white until there's nothing left and we're left with black. So there's the two major theories. Those theories developed by Sir Isaac Newton. We learned about how our eye interprets color, that we've got red, green, and blue cones in our eyes that get stimulated. That stimulation correlates to how we see and how we experience color. Then we talked about lightness, chroma, and hue. We talked about those, how those three are different. And then we talked about a spectrophotometer, and the spectrophotometer, how it measures and documents color based on lightness, chroma, and hue. And we talked about the two color spaces. We've got CIE LAB and CLCH. So, and the final takeaway from it is that a CIE LAB or CLCH is a much better way of documenting color and communicating it, because whenever we do that, it's not being impacted by the device that creates that color. All right, so that's a quick wrap up right there. Hope I didn't bore you too much. Thank you very much, and we'll work more on this as we move forward through the class. Thank you.